So today we are talking about assignment number 1, and as you have probably seen by now the announcement I made on Discord and D2L, I've decided not to go with C++ for the assignments this term after, trust me, a lot of hours, a lot more hours than you probably imagine. The assignments were becoming a little bit too much about the low-level stuff, which is great for people like me who really love the low-level stuff. But this is an algorithms course, and I want to focus on the higher-level algorithm stuff. And I think that JavaScript is just a better language to do that right now. Maybe when I have more time over the summer, I'll be able to make the assignments in a nicer way in C++. So apologies to those of you who have already looked at the C++ lectures. I'm sorry that you had to go learn for a couple of hours, but at least now you know a little bit about C++, right? Okay, so as you see that I've also kind of switched around the order of lectures a bit because we no longer have that other lecture which is specifically about C++ and setting things up and the optimizations and stuff for C++. So without further ado, let's get into the assignment. So assignment number 1 is about breadth first search, depth first search. What I'm going to do is I'm going to give a demo of the assignment, and then I have slides that go over the details of the assignment, and then I will go over the code of the assignment at the end. So a quick note at the beginning is that you will all receive by midnight tonight an email to your @mun.ca email address with links to download all 5 assignments. Those links only become active as the assignments are released. And so you'll get that assignment at some point this evening. I'll make a D2L announcement and a Discord announcement when they're available, but then you'll be able to click on the first link and download that assignment. And again, it will have embedded in all the files your name, student name, email address, both in hidden text and in plain text. So please only share your assignment files with the other person in your group if you're working in a group of 2. And if you are still not sure whether or not you want to work with somebody, so who here wants to have a partner for the assignments but doesn't have one yet? Can you put up your hand if that's the case? Okay, so sure. Well, there you go, right next to each other. If you do want a partner for the assignments, just please meet outside and say, hey, you look interesting, I'll have you for my partner for the assignment. On Discord, there is also an LFG, that means looking for group channel, so you are free to post on the Discord or look at the class list and contact someone. But it's up to you to form groups for the assignments. With that being said, let's get into the demo for the assignment. So this here is the assignment as it is given to you. Sorry, there's someone who's talking. Can you please not talk while I'm explaining things? It's quite distracting. So here is the demo for the assignment. The assignment is written in HTML, CSS, JavaScript, and it uses HTML canvas to draw this environment to the screen. You do not need to know anything about how the user interface works. However, all the code for the user interface is there if you are curious and you just want to see how it works. I will not be really going into any of the details of how the user interface works, other than to say this user interface is being updated 60 times per second. And so when you do things like click on the animated visualization, which is what I'll get into in a little bit, that is being refreshed at 60 times per second. So that's the only real reason why the UI matters whatsoever. This is a grid world. Let me go into a bit of a bigger one just to show you here. This is a world that's separated into tiles, and it has a size. So for example here, this one says L-shaped wall 16 by 16. So in this environment, we have an XY grid, and as you move your mouse around, you can see that your cursor, like where the cursor is, gets highlighted. So if you click on one location, and then you click on another location, you have set the start and end point for a search algorithm. And then ideally what will happen is that your algorithm will run, and then you'll see a path be returned by your algorithm. Now, this is the student BFS version of the algorithm. You can see here we have student BFS, student DFS, and student ID-DFS. So those are the three algorithms that you'll be writing for assignment number 1. It's a shockingly small amount of code. And then we have solution BFS, solution DFS, and solution ID-DFS. So I will be giving solution code for this assignment, but that solution code will be obfuscated. So there are obfuscators out there for JavaScript where I put it in and it gives you back this like garbled mess of code. It is possible to de-obfuscate that solution code in a way that is sort of readable, but if you do that, you're really only selling yourself short because I've done the assignment in a slightly different way. So if you do that, it's just, if you de-obfuscate things and try and learn from it, it's really a lot more work than just doing it from the slides. Because as you will see, I am basically giving you the code in the slides. Assignment 1 is all about just you getting used to this environment, getting used to JavaScript, and programming some simple examples. So the student code that I give you is basically incomplete. So if you look here, for example, this solution code goes through walls, right? So it doesn't actually do the search. It just goes over and then goes down. If I look at the solution code, it actually does do the search. So what you're seeing here is there are a number of different colors on this map. So if I go back to the default environment, and then I'm going to click toggle grid, so it turns off the grid. So however you prefer to visualize this with or without the grid, you can turn that on or off. All the grid is it draws some lines. There are different colors here. Those colors are essentially arbitrary. The way that this is represented under the hood is that it's just a 2D array of integers. Okay? So for example, gray might be 0, green might be 1, blue might be 2, or any combination of those. I can't exactly remember. But I've just assigned arbitrary colors to those integers to make it sort of interesting and intuitive to look at. Okay? But what these colors mean, like the fact that it looks like water, that it looks like a rock, that it looks like grass, has absolutely no bearing on the assignment. It's just for your own intuitive purposes. The only reason it matters is that you cannot pathfind between two things of the same color. So I cannot walk from blue to green, or green to blue, or gray to green. So for example here, if I click here and then here, okay, now there's some more colors. What do those colors mean? The white color, that is the path, right, from the start to the goal. The red color are the states that are in the closed list. So those are the states that we have expanded. And the yellow ones, those are states that are in the open list that have not yet been expanded. Okay? Now, if you just hit refresh, it says all of this down here. So if you forget, all of this is down here. Okay? So an object can only move through the colors of the same tile. Click any drop-down menu to change the settings. Click the animated search visualization. Okay, let's do that next. So if I click animated search, and then I click, let's do this on the L-shaped path, L-shaped wall. So if I click here, then I click here, the animated search, oh, sorry, I've got to do the solution. It will show you what's happening as the search is going on. So this is the actual expansion of the open and closed list that eventually leads to the path. And this is very good for debugging. And if you then come down to the ultimate in debugging, you can click this single step, then click rerun previous path to reset it. This other one is just where my mouse last was, this little bug in the UI. But if my mouse goes off, it just highlights the last tile that it was touching. Then what I can do is I can hit single step, and you will see a single expansion each time. Okay, so you can use this to help debug your algorithm. Now, you may say, oh, sometimes I hit single step, a new red one does not appear. And that's the case where the node that I've taken off the open list is already on the closed list. So it hasn't added a new one to the closed list. Okay, and I'll get into how all that works in a bit. But this is how you can just help debug your stuff. Okay, and so there's 4 levels of visualization. In one of them, the UI will run your algorithm to completion and then display the final path. In another one, it's the same thing. However, it just doesn't draw the open and closed list. And so it only draws the path. The reason this is useful is because if you come over here to like one of the bigger maps and you click and drag, if you do that, let me turn off the grid. If you do that for one of the larger maps, the drawing of all these red tiles, that's what's sort of lagging. here. It's the drawing of it, not the actual computation. So if I come down here and turn off the drawing of the open and closed list, now this is much faster, much smoother. Okay, so that's why I have that there. And then there's animated search and there's single step. So that's what those visualizations are. Here you can see that there's two other options. There's object size and there's legal actions. But these are grayed out for assignment 1. The reason is that in assignment 2, we will be talking about objects of different sizes, and we'll be talking about different action types. So in assignment 2, we'll be doing octile movement, which is 8 directions. For assignment 1, we only have 4 directions, up, down, left, and right. And of course, we can also select these things. Now, if I go over here and I click Run Tests, then for the default map and for the Wheel of War, the really big map, I have included some tests. So if I click Run Tests here, you'll see this table appear, and I know that's impossibly small for you to read as you're sitting there. But what this does is I've hard-coded in 20 start and goal locations that I think are interesting, and it will run the solution and tell you the path cost for the solution, and it will tell you the running time in milliseconds for the solution. Then it will also run your code, tell you what your algorithm said, and what your running time for that was. Now you can see here that by default, some of these are actually correct, right? And those are cases where, well, student BFS, if I click here to here, that's obviously incorrect, right? Because I haven't actually done the search. I've just returned a path that's like just an example path. But if I do it from here to here, that actually is the correct path. Okay? So if all you do is hand in what I gave you, you're not going to get 7 out of 20 marks, right? But it's just some of the tests are cases like that where there's no obstacles in the way. Okay? And in the case where you have no path found, like down here, then these costs are -1. And so if no path is found, then the cost of that path is -1, just to show sort of a failure. And I think that's about it for explaining this. Oh, there's also random tests, and this will just choose random points on the map. So here, for example, what it will do is where it says solution path, that will run the solution. And where it says student path, that actually runs the currently selected algorithm. So if I run solution run tests, they're all correct because it's running the solution versus the solution. Okay? So student path here should probably be selected algorithm. And the last thing I will show is up here we have depth first search. So solution depth first search. When I said that depth first search is wonky, I wasn't lying. That's what depth first search looks like. It's just absolutely insane. It just goes down until it finds the goal. Depth first search will not be graded for path cost because it's not optimal. So do not run the tests with DFS. It makes no sense. DFS is not guaranteed anything. And so the only thing that we'll be testing on DFS is whether or not you found a path. Okay, so if the path exists, good. If not, no. And for iterative deepening depth first search, iterative deepening depth first search is probably going to be, in practice, much slower than your breadth first search. But what I want to happen for iterative deepening depth first search, let me just refresh this and go to a smaller map. So if I go over to iterative deepening depth first search, and then I go to animated search, what we're going to be judging with ID-DFS is the following behavior, where it sort of, you can see it resetting and then going to a new depth, resetting and going to a new depth, resetting and going to a new depth, until it actually gets to the goal. So if I speed this up, eventually, it does get to the goal, okay? All right. So what I'm going to do now is, also, how I recommend actually doing these assignments. How is it actually set up? So this assignment is, like I said, it's HTML, JavaScript, CSS. So when you get the assignment, and I know this is quite small, and you can't actually read the names of these files, you'll get a zip file. In that zip file, there'll be an HTML file and some JavaScript files. That's all. So if you just right-click, well, in Windows, if you, I recommend using vscode, so Visual Studio Code. That is completely different from Visual Studio. Do not install Visual Studio. That is not what you're using. I recommend VS Code, but you could literally do this in any text editor. If you want Vim, if you want Emacs, Notepad, whatever. As long as it opens a text file, you can edit the JavaScript files. So what I do here is in Windows, if you install VS Code, you can just say open a folder with VS Code, and now you're editing all the files in that folder. Okay, so that's it. All you have to do is take a JavaScript file, which I'll go over at the end of the lecture. You make some changes, you hit save, then all you have to do is come back over to your HTML file and hit refresh. And then all of your changes should be refreshed. Okay? So as long as you open the HTML file in a browser, that's all you need to do. I've seen some students in the past sort of set up a local web server to like serve the file. If some people who did it in like Xcode, if you hit run, it like runs a local web server or some nonsense. Literally, just open the HTML file in any browser. I will say that even though I'm a big fan of Firefox because it's open source, the code does run much faster in Chrome because Chrome's JavaScript engine is faster, and we will be using Chrome for the marking of the assignments. So just give it a test in Chrome to make sure everything works. But I've never seen anyone do anything that worked in one browser and didn't do it in another browser. But don't try to be the first person to do that. All the JavaScript should be completely cross-platform. So that's how you do it in Windows, and I'm running Windows in a virtual machine right here, so I'm doing the same thing in a Mac right now. But this is a Mac natively, so I'm going to use the Mac for the remainder of the lecture. So let's go into the PowerPoint slides in which I will explain the nitty-gritty of the details of the assignment. So let me get my laser pointer here. All right, so assignment number 1. Watch the demo first. That was just a reminder to myself in case I opened these and hadn't done the demo. So assignment 1 is using JavaScript and HTML. You are given the UI. You just have to implement the algorithm. It's pathfinding using BFS and DFS. It is 4-directional grid movement only, so up, down, left, and right. The goal is to implement BFS and DFS. And for 6980 version of the course, you're also implementing iterative deepening depth-first search. And the little bit of thinking you have to do for ID-DFS is probably going to be the main troublemaker for the assignment, but still, it's not a difficult assignment. Don't worry if you don't know a lot of JavaScript. JavaScript is very similar to Java, Python, other languages in its basic syntax. All you're going to need to know, basic programming like variables, object using, for and while loops, if statements, 2D arrays, which are just arrays of arrays, functions and classes, like very basic stuff. There is nothing JavaScript specific that you need to know. Now, there are sometimes things you can do in JavaScript, like give objects a global scope instead of a local scope like you're used to. Basically, as long as whenever you declare a variable in JavaScript, you say let variable equal 5, instead of saying var variable equals 5. So my rule is use let, not var, and you should be fine. Let is the normal standard block scope that you're used to. Var is this weird global scope where you can declare 2 variables of the same name in the same scope, and it's totally weird. JavaScript can get wonky if you do things in a weird way, but we'll get into that a little more at the end. So I used years ago this series to learn how to program in Canvas. It is kind of outdated right now, but I just kind of wanted to link you to it in case you're really interested. Hey, that's a nice user interface. I would like to make one of those one day. So there's many tutorials out there. That just happens to be the one that I used. I'm not affiliated with them. I don't get any sponsorship or anything like that. That's just the link that I used. But it's completely outdated and not necessary whatsoever. So here is the user interface that I just showed, and I showed you how to interact with that via the mouse and stuff. But let's have a little zoom in. So we are operating on this grid world, and the grid world essentially consists of these XY states. Now, you're probably used to the standard Cartesian coordinates where 0, 0 is in the bottom left corner, x goes up to the right, and y goes up vertically. The only difference in this course is that most computer graphics systems operate with 0, 0 in the top left corner. Okay? So the y has flipped. That's it. So if you want to go down, you have to add 1 to y. If you want to go up, you have to subtract 1 from y. That's the only difference from what you're used to in terms of standard Cartesian coordinates. And a state in this environment, because the environment is completely static, nothing will ever change in the environment except the location of the agent. And so this is what we think of as a state. It is just an xy location in the environment. And for assignment 1, the object, or the agent, only occupies 1 tile. In assignment 2, we'll get into what happens if the agent is actually bigger, right? But for right now, it just occupies 1 tile in the environment. Actions are going to be represented as an array of length 2, where the first element is the x change and the second element is the y change. So in JavaScript, we can just say let action equal bracket x comma y. We've got an array really easily. And so moving up is 0, negative 1. Moving down is 0, 1. Moving right is 1, 0. And moving left is negative 1, 0. Right? Really easy. That's how we specify the actions. And to get from the current state to the next state, we just take the xy of the current state and we add it to the x and y of the action. That's it. And the only weird thing here is that we'll have a state as part of a node, right? So a node will have an x and a y. So you'll have to say like node.x plus state 0. And that'll give you the x of the next state. And I'll go into that when we get into the code. These are the costs of our actions in this assignment. Now, you might say, why are the costs 100? Shouldn't the cost be 1? Yes. But when we get to assignment 2 and we start talking about diagonal actions are, even though these are rectangles here because I was lazy when I was drawing them, they're actually squares, right? So the cost of a diagonal action would be the square root of 2, which is like 1.14 or 1.412 blah, 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 right? Irrational number. But I wanted to keep things easy so that we wouldn't have any floating point errors. So I wanted to have all integer costs. So when we get to assignment 2, I basically multiplied everything by 100 and rounded it off. So instead of having a cost of 1.412 for a diagonal movement, we're going to have a cost of 141. It's just a good approximation, but it's all integers, which will help you in this course. And it also helps me because I don't have to type infinitely long floating point numbers onto my slides. So all I did was I took the costs, which is the distance of the movement, multiply it by 100, and then round it off to the integer. Okay? So that's why we're just taking, for assignment 1, an action is just cost 100. All actions have cost the same, and since all actions have the same cost, BFS will be optimal. Right? That's one of the things. So BFS will be optimal in this case. It will return the optimal 4-directional path. There are some conditions on the action legality, which I've already talked about a little bit. But first, the object must be entirely within the map bounds. So if the default map has size 64 by 64, then the x and y values must be between 0 and 63. Okay? Because, of course, our arrays start at 0. Now, this will come into play a little bit more in assignment 2 when our object has a size. Right? So if part of that object is larger and it overlaps with the side of the map, that can't happen either. So that's a little bit more important in assignment 2, but obviously it has to be within the environment. The object can move in 4 directions, up, down, left, and right. The object can only move to a space if it is the same color as where it is currently, and an object cannot move off of the map. So if you are on the very right-hand side of the map, going right is not a legal action. If you're at the very top of the map, going up is not a legal action. So when we write our isLegalAction function in our code, which takes in an xy state and an action, these are the things that you have to check. And in assignment 1, you have an object of size 1, which just occupies 1 grid cell. That's it. So that's not super interesting, but I just wanted to demonstrate that. Here are the legal actions. So if your object is currently right here, the possible actions are up, down, left, and right. But in this case, you can move up, you can move right, you can move down, but you cannot move left. That is false because you can't move to a tile of a different color. So that's just an example of that. So once you run your search algorithm, you're going to come up with a path and that path is going to have a cost. So what is that? So for assignment 1, each action has cost 100 for all possible actions. The path cost then is going to be the sum of all the actions. And so you can take a nice little shortcut for assignment 1 where we don't need to keep track of our cost over time because you can just take the path length and multiply it by 100 to get your path cost. If no path is possible, meaning that we have run out of things in the open list and haven't yet found the solution, then you are going to set the cost to -1 and you're going to set the path to empty. But the path should already be empty, so you won't really have anything to do. In assignment 2, we're going to have cardinal actions be 100 cost, just like assignment 1, but we're also going to have diagonal actions. And now you know why this is 141, because it's essentially square root of 2 times 100. How do you obtain the final path? Well, once you've selected a node from the open list that contains the goal state, you have to construct the path that got you there. So you've seen a node, you've checked the state, and the xy of the state of the node are the same as the goal location. So you know that you've reached the goal. So paths are a sequence of actions, not a sequence of states. Okay, so that's a little problem that some people have, is that they construct their path as a list of places you've been, but think about the path as a sequence of directions rather than the sequence of places. So for example, if your path was down, down, right, then this is how that path would look in JavaScript. Right? It's an array of arrays of actions. And so what you have to do is, once you get to the node, nodes are going to have a parent pointer to the parent of that node, which is another node. You follow the parent pointers from the goal node back to the root node of the search tree. So let's have a look at what that looks like visually. Let's say we've gotten to the goal node down here. Let's just ignore the fact that we reached the goal here. We're just at this particular node in the search tree. This node is going to have an x and a y and a parent, and also a depth, but we'll get to that in a bit. So we've reached this node, and now what we do, in order to go back to find the path, what we can do is say, look at the parent. If the parent exists, take the action that got us there. If the parent exists, take the action that got us there. Look back, if the parent exists, take the action that got us there. And now there's no parent of this node. That parent is null. We're going to set the parent of the root node to null. And once we see that the parent is null, that's how we know how to stop this backwards traversal. So I included a little bit of pseudocode there. So if you wanted a pseudocode to compute the path leading to a particular node, well, you just have an empty path, and then you say, while the node has a parent, add the action of the node to the path, and then set node equal to its parent. And then so that loop will take care of everything for you. And as some of you may have already noticed, if you go backwards, adding actions to the path, you've actually added the actions in reverse, so then you need to reverse the array. And it turns out that JavaScript in all its glory has a dot reverse function on arrays, and so you don't even need to write that function. And then that's the path. Now, the only thing that we haven't talked about yet is the node class. And so this is the exact code for the node class in JavaScript. Classes in JavaScript are quite like any other language that you've seen. So we just declare class node, then we explicitly declare a constructor. So this constructor is going to take in the x and y, that's the state of the node, then the action that got you to that node, and then the parent. And so it sets this dot x, this dot y. If you're used to Python and you've never done JavaScript, this dot is essentially the self dot of Python. It refers to the object instantiated currently. Then you set the action, you set the parent, and the only other thing is that for iterative deepening depth-first search, you're going to want to know what depth you're at. And so let's just store that in the node. Makes sense, right? So if we go back a couple of slides, whether or not you start the root node at depth 0 or depth 1 doesn't really matter, right? You're just increasing the maximum depth by 1. So maybe this is depth 1, this is depth 2, this is depth 3, this is depth 4. So how do we know the depth of a node? Well, that's pretty easy. It's just the depth of the parent plus 1. So this just says, okay, if the parent is null, it means that it has no parent, and so let's set the depth to 0 or 1 or whatever you want it to be. Otherwise, a parent exists, so take the depth of the parent and just add 1. Okay, so that's the constructor. It does the depth for you. You don't need to specify the depth. But the only important thing here is that for the root node, you must specify the parent as null. There are a number of different ways in JavaScript for it to like say that things don't exist. One is undefined, one is null, one is I can't remember if this is like an unknown or not a number, or like there's all sorts of different error codes. We're just going to use null for everything, okay, that we don't want to happen. And so node.depth is going to be very helpful for iterative deepening depth first search. The algorithm that you're going to write is right here. We've already looked at this. This is the BFS, and you're just going to take this and translate it into JavaScript, right? So for example, if node.state in closed, well, whatever data structure that you've implemented your closed list in, you're just going to look over that closed list and see if the state is in there, okay? One thing to note that's super annoying is that when you check for state equality, so let's say you have like a state in the closed list represented by an XY array, and then you have a state over here represented by another XY array. If you say, does this array equal this other array, the answer will always be false, because they are literally different arrays. They just happen to contain the same values. So what you have to do when you compare two arrays in JavaScript is say, does the x value of this one equal the x value of that one, and does the y value of this one equal the y value of that one? Or is the first, is index 0 equal to index 0, is index 1 equal to index 1? That trips a lot of people up sometimes, and it gets their closed list not to work. You'll very quickly see that your closed list doesn't work if your algorithm doesn't find paths greater than length like 5 or 6. So if you run your algorithm and you're getting really small paths easily, but then when you click on the other side of the map, it seems to crash or hang, that means that your closed list isn't working. Because the closed list is the exponential reduction in time complexity, right? Okay, so this is the algorithm. And how are we going to do this in the code? Well, we're going to have a number of different functions. In the assignment, we have a function called searchIteration. And I'll go over this when we get to the code. But the searchIteration function essentially does everything in red here that's inside this while loop. The user interface provides the while loop for you. Okay? So in order to be able to do things like that single step and the animate, the UI is in control of when your searchIteration function gets called. If you just wrote the while loop here, it would do the whole search, and you wouldn't be able to have that nicely debugging animation. So you are going to write in the searchIteration function whatever goes inside the while loop here. So all this red stuff. And then in the startSearch function, that's what goes up here. Whenever we start a new search, we have to do some things like reset the closed list, reset the open list, maybe set some other variables. Okay? And then for depth first search, it's the exact same algorithm, except you've got a stack instead of a queue. Okay? And so the same thing goes. In fact, as we'll see when I get into the code, there's going to be one line of code difference between your DFS and BFS. Now, down here in expand, some people write that expand function as its own function. Some people write the expand function in a loop right there in the code. I don't care which one you do. If you just want to say, for each action, see if it's a legal action, add it to the state, get a new node, add it to the open list, all that can be right there inside that loop if you want to. It doesn't matter. But I've just given you some pseudocode. So remember, so if you want to expand a node, you just say, for every action in what my legal actions are, create a new state by adding the action to the node's state. So this isn't literally JavaScript, right? This is just pseudocode. In your code, you'll say new x equals node.state.x plus a0, right? It just looks a little bit different, but the pseudocode is the same. And then I'm intentionally skipping a line here. And then new node equals new node. You pass in the state the action in the node. In fact, our node has x, y action node. And then you add the new node to the open list. That's it. And so if you want to write that in its own function, if you want to just put those few lines of code here, I'm not going to dock marks for either of those. However, there is a little optimization that you can do here. It's a memory optimization where, remember in our code where we said, hey, when we get a node from the open list, if it's in the closed list, don't look at it, right? Now, one thing that you have to be sure of, here, I forgot to say this. Here I'm saying things like return fail. Since this is in its own function, you just return. If there's a failure, you just say, okay, the search is over, set the path cost to -1, return. You're not actually returning a failure. Here, you don't actually return a solution. We will see that our class is going to have a this.path. It's going to have a this.cost. You just set those and then return. Here, where it says if node.stateEnclosed continue, that's because we're in a loop. But since you are not in a loop in your actual code, this will be a return. Okay, so it'll say if the node is in the closed list, return. However, another optimization you can do is when you generate a new state, you can check to see if that state is in the closed list, and then don't add it to the open list if it's already in the closed list. Because if you think about it, when we generate the state, we put it in the open list. If it's ever taken from the open list, we will just check it against the closed list and then throw it away. So this is a slight memory optimization. In some cases, it can be a huge benefit. In some cases, it's not. But it all depends on how efficient your closed list is. Right? If your closed list, if it takes a long time to look up something in the closed list, maybe this actually won't save you anything. It'll run slower, but it'll just save a little bit of memory. So that's up to you. So assignment 1, BFS and DFS, they're both done in the search iteration function and should only differ by one line of code. And I'll show you that line of code in a second. And oh, here it is. So you can implement your open list however you want. I'm not imposing an open list on you, but what I highly recommend is just use a JavaScript array. Because JavaScript arrays, if you use push, you push to the end of the array, which is what you want to do in both a stack or a queue. If you want to remove from the end of the array, you use array.pop. And if you want to remove from the beginning of the array, you can use array.shift. So all you got to do is say, if it's BFS, use shift. If it's DFS, use pop. And the rest of the algorithm is identical. So it's literally one line of code that's different between BFS and DFS. BFS should pass the tests. DFS will not pass the tests, okay, because it's not an optimal algorithm. Not optimal even when path costs are the same. DFS path costs will not necessarily match the path. Man, this is a tongue twister. DFS path costs will not necessarily match the path costs of solution DFS. So all I care about for DFS is that there is a path. That's it. All right. Iterative deepening depth first search. ID-DFS will be significantly different from BFS or DFS. You've got a bunch of different things going on. So it's going to have its own function. It has its own search iteration function. So I've included this searchIterationIDDFS, and I've just put it in there. If the method is ID-DFS, call that function instead. So you can put all of your ID-DFS code there. And then it says, see the tips inside the class, and I'll get to those in a bit. The ID-DFS should animate properly, like I showed in the slides. So ID-DFS is going to a depth, then resetting, going to a depth, then resetting, going to a depth, then resetting. I should see that. That's how we're testing your ID-DFS. In practice, it will be much slower than breadth first search, okay? Because you have to reset the closed list, and it takes time to do that sort of thing. You may need to add additional class variables to the student search class. That's fine. You can add whatever you want to that class, as long as you do not rename any existing variables. Because if you rename existing variables that are used by the user interface, then it will crash. Okay, so just don't rename anything, but add whatever you want. ID-DFS should produce paths the same length as BFS, but probably a little bit slower. Okay. Some grading notes. Only BFS will be tested using the run tests. DFS will only be tested by visual inspection to make sure a path exists. It's okay if your paths look different than the solution paths. The only thing that matters is that the costs are the same, right? Because we can go right then down, or we can go down then right. The way that those two are generated depends on the order in which you iterated through the actions, which doesn't matter to me. Okay? The only thing that matters is that you got an optimal path, not the same optimal path. Some quick JavaScript notes. Use let to create variables, not var. So let node equals new node. Do that. Do not say var node equals new node. Var uses a strange scope, can cause logical errors. I have had people almost in tears in my office before, not understanding how their assignment is broken. It's causing errors, it's not working, but they swear that it's working properly. I changed var to let, and it worked, and they wanted to smash the table. Like, it's very frustrating. Trust me, do not use var. You can cause a headache for yourself. It could be fine. It could work perfectly well. But if you go read up on let versus var, you will understand the pain. I suggest always testing your code with the debug console window open. Now, here, Control-Shift-J opens the debug window in Chrome. It's Control-Shift-K in Firefox, but it's actually Control-Shift-J in Firefox in a Mac. It's weird. You can just hit F12 and then open the console. I'll show you that in a bit. If you want to use print statements to debug, so you can do one of two things to debug your assignments. There is a built-in JavaScript debugger in both Firefox and Chrome. Go watch a YouTube tutorial on that. I do not have time to teach that debugger. If you want to use that, you can. However, the old tried and true method of print statements, console.log. If you say print, it will actually try and print the web page with your printer. So like the print with a printer dialog will open. It's console.log, and then it will show up there. A cool thing about the console is that you can print objects. If I print out a node, it will let me look at all the variables of a node, just like a debugger. However, one thing to keep in mind is, let's say, for example, I print out the open list, which you can do, and then you'll be able to look through it and see all the things in it. If you print out the open list, and then you make a change to the open list, and then you print out the open list again, the print statement just makes, like, it prints the pointer to that thing. So if you're printing out the same object at two different times, you will only see the most recent version of that object. If you want to print it out and have sort of a history of what it contained, you'll have to make it into a string somehow. So you can say json.stringify this.open and print that string, because it turned it into a string, then you printed the string. But if you print objects, then what you're looking at is how the object is right now in memory, not how it was when you printed it. Okay? But if you print integers or if you print strings, they will be as they were when they printed it. That's just a really weird note. Okay. Any red message in the console means that there is an error. You will have errors at some point. If you get through this whole assignment without having an error, I applaud you. I couldn't do it. Even if your answer is somehow correct, you are wrong if there are red messages. Okay? If one thing that happens, for example, is you tried to run a search and the grid lines disappeared from the UI, or the mouse stopped working, that is because you have an error and you don't have the console open. Okay? If the UI breaks, you will see an error. The only reason things will break and you won't see an error is if you have an infinite loop, or if your closed list isn't working and it's searching all possible paths without a closed list. So if you're currently looping for a long time, that's the only reason it will break. But if the mouse, if things look okay, but it's not working, it's probably because you have an error message. Error messages are bad. Do not, under any circumstances, try and get rid of the error messages using try-catch. Okay? You can take a whole JavaScript class, wrap it in a try-catch, and then you'll never see any error messages. But the only thing you're accomplishing is that you won't see them. They're still happening. Don't use try-catch. We will use try-catch in one very specific example for assignment 3, but that is to accomplish a goal, not to hide an error message. Error messages are bad. They will lose you marks, even if all your tests pass, because it means that something is wrong. One of the most common errors is that, for example, you're checking something out of bounds. Right? If you check something out of bounds, it'll come back trying to check blah, blah, blah of undefined. So something you have is undefined. You can see there, you can click it, you can look at the call stack, you can see what function you're in the debug window. It's a really good debugger. Okay, so that's it for the slides. Now we are going to move into the code. So I have vscode open here, and I am committing the unforgivable sin of using light mode, but it shows up a lot better in the video. Okay, so I apologize for using light mode. Don't hate me, but it's almost impossible to see the dark mode text here. Let me take a drink real quick. Are there any questions about anything I have said that didn't make sense? Perfect. Okay. So when you get your assignment, it will contain a number of files. In Visual Studio Code, which I recommend, you could, like I said before, you don't have to use VS Code. You can use whatever you want. However, I think it's very well suited for this. It has JavaScript, syntax highlighting right out of the box. It's easy to install. You don't need to like fool around with any settings. It just works. So what you can do is File, Open Folder, and then open your assignment folder. And then over here on the left, you'll see all the files in your assignment. Super, super easy. So I'll go through all these files here, and the last one we'll look at, we'll stick on that because that'll be the thing you have to edit. So the first file is the HTML file. That just sets up the web page. Everything, all the GUI stuff is basically done using JavaScript. I use JavaScript to insert things into the HTML file. So that's it. It just sets up the CSS. It's pretty boring, pretty basic, and it imports all the JavaScript files. That's it. Next, let's look at environment. This is something that you will have to be concerned with, because this is how your environment is actually represented. So I have an environment class here, and this has a getXY function. So if I look down, how are the environments actually represented? They are just long strings of characters. Okay, that's the, like, JavaScript cannot read from local files on your hard drive, so I just had to encode these in the JavaScript in sort of a janky way, but whatever, it works. So each of these environments has a name. The name is what shows up in the HTML file. So I come over here, this is default, and then it appends the like, let me see if I can get this a bit bigger for you. Nope, there we go. So you can see up here, it uses the name, and then it appends the width and the height to the end of that string. And when you select one, it just selects the proper one. So over here, each environment has a width and a height. Some of them have tests defined, and so those are where the tests come from. And in here, you can actually see the correct answer. So I've hard-coded the correct answer in here as well. I will be checking if all you're doing is looking up the correct answer and printing it out. So don't try that trick, right? That's just there in case I didn't want to give you the solution code. The answers would still be there for you to look at. So here are all the different environments. And what I do here is I basically have a class that wraps that data. And the only things you're going to need to know for those environments are possibly the width, the height, and how to get, and is it out of bounds. Okay? So get XY, well, these things are encoded as a 1D array. So in order to translate the two-dimensional x and y into a 1D array, it's just y times width plus x. That's just the formula to get the thing from 2D to 1D. You don't need to worry about that. It just gives you what you want. And is out of bounds checks to see if the x and y, if they're less than 0, or if they're greater than the width, then that's not good, right? So that's out of bounds. So is out of bounds is sort of a negative check. If it's out of bounds, you want to say this is not legal. Okay, so those are the two functions there that are written for you. You don't need to worry about those functions. And so in your code over here, which I'll show for 1 second, I got to make sure I'm not clicking on the solution here because it's being recorded. Okay, this.grid, okay, I should name that to this.env. This will either say this.grid or this.env by the time you get it for the environment. You will say this dot that variable dot get xy. So this dot grid dot get xy or this dot grid dot get or is out of bounds. So that's the variable there. Okay, the next file that we will look at is the user interface. This is the 600 lines of code that does the user interface. You never have to open that. You never have to modify it unless you absolutely want to. But just keep in mind that the only file you're submitting is the search file. So if for some reason you did something crazy to the UI, it will not be submitted to me. It will only be accepting a single JS file, and that will be searchStudent.js. Okay? Next is the solution code, which is obfuscated. Okay, so this is what the solution code looks like. It's not a perfect obfuscation, but just keep in mind as well, when I talk about timing stuff, if we go back here and look at, for example, when I click Run Tests, oh, hang on. When I click Run Tests on a map that actually has tests, you can see, let's go to a different map, Wheel of War. All right, so this is a harder one because it's a bigger one, right? It's 16 times as big as the original one, so bigger maps take longer to search. You can see here, for example, that this search with the solution took 9 milliseconds. This one took 5 milliseconds. This one took 6 milliseconds. If I come over here and I select Solution BFS and do this, you can see that path took 5 milliseconds. It was actually searching 7 million nodes per second. Okay? So that's the solution code. My solution code is a little bit optimized. You may not be as fast as the solution code. But because I can't give you the solution code, I have to give you the obfuscated solution code. The real downside of the obfuscated solution code is the way that it does it slows down the running of the code dramatically. So my obfuscated solution code that you will get is between 5 and 10 times slower than my actual solution code. But matching the obfuscated solution code time is actually pretty good. Okay? So if I go back here and I run the tests, okay, so this ran the tests in 45 milliseconds using the solution code, like the unobfuscated solution code. If I come back and I change the HTML file to actually use the obfuscated solution code, and I rerun those tests, so what was it, 45 milliseconds? Yeah, now it's 823 milliseconds. So it's almost 20 times as slow. Because what it does is it puts the code it codes it into strings, in arrays, and then it has to unstringify the code, and so it's bad. But I got to give you something, right, so that it can run the tests, so that you can see what the solution code looks like. So just realize that if you match this time, I'll be very happy. And actually, I think what I said was in the solution file, if you run the tests here and every path is less than a second, I'm fine with that. Right? It doesn't need to be sub-millisecond like my solution code is. If you get anywhere near the obfuscated solution code running time, I'm perfectly fine with that, as long as it runs reasonably fast. Well, fast enough for us to mark. We don't want to be waiting around 10 minutes for your code to run. So that's the obfuscated solution code. That is what you will receive. Just keep in mind that if you're like, yay, I beat the prof, well, you still got 20 times as fast to go before you actually beat the prof, right? And my code can be beaten. It's just, yeah. All right. So the last file is the most important one by far. This is the search_student.js file, which contains the search_student class, and at the very bottom, the node class. So the node class is at the bottom. You can use that for your algorithm. If you say let node equals new node, that is what you'll be using. And just keep in mind that it's x, y, action, parent. That's the order of the variables passed into the constructor. So how long do I have? What time is it? It is 2:55. I've got about 20 minutes. OK, we should be good. So in the search class, it gets passed in a grid. That is the environment. And it gets passed in a config. So config is relevant to you. This .config stores 3 variables. It stores the actions. So this .config.actions, that's where the legal up, down, left, and right actions are stored. You should read from those actions. You don't need to create that array yourself. It also stores action costs. This will be more relevant for assignment 2, because in assignment 1, you can just multiply your path length by 100. But in assignment 2, we will need to use that. So you can skip that one for this one. And this will be config.strategy, which is this or ID-DFS, right? So if this .config.strategy equals that, that's the search algorithm that you do, but I've already got code for you there. This .grid, that may be renamed by the time you get it to like this .env or something like that, but that is the environment class that contains the actual data where you can look it up, because you need to say, is this value the same as the other value? Here we have the starting x and y and the goal x and y. These are currently set to -1. These are set by the mouse. You don't need to worry about that. You assume they will contain, whenever you start a search, they will be valid. The UI takes care of that. This .cost starts out as 0. And when you build a path, when you find a solution, you set that cost to the path length times 100. Or if you find that the open list is empty and there is no path, you set that to -1. And that will make you pass the tests. This is an important one, this .inProgress. So when we had the slides open, there was a while loop in the BFS code. That while loop is now inside the UI, and that's what it uses to either keep doing the search or stop doing the search. Okay? So this .inProgress, when a search starts, that's set to true. When you stop your search, you set that to false. That's it. That's all you got to do. This .name, ignore that for now. That'll be relevant in future assignments. Something I wanted to do but never ended up happening. Here you have this .path, this .open, this .closed. What I recommend, start the assignment, just have the open list be a JavaScript array, use pop and shift. Just have the closed list be a JavaScript array. Just look through it to try and find if a state is in there. Once you get everything working with this basic setup, then if you want to try and optimize it to make it faster, only do it then. Get it working, submit it, then try and optimize it more if you want to. Only the last submission that you make will be taken. Okay? You can have whatever data structures you want for the open and closed list. In fact, what I sometimes recommend is the separation of code from storage logic. So if you want to create an open list class and use that open list class, feel free to do it. If you want to create a closed list class, right, where all you have to say is closed.contains or closed.insert, by all means, create your own classes. The only thing is they have to be in the same file. But JavaScript allows that, right? So I can just say class open list, and there, now I have an open list class. And I can create functions on that, so I can say insert, this will be a node, that's a function. Super easy, right? So you can even create your own class if you want to, and I actually kind of recommend it. But by default, they're just arrays. Next function, we have startSearch. So startSearch, this function should set up all the necessary data structures to start a new search. This includes, but is not limited to, setting the start and goal locations, resetting the open and closed list, and resetting the path. I've provided a starting point, but it is not complete. So startSearch is going to take in the starting x and y, the goal x and y, and so what I do here for you is, okay, there's a new search in progress. Set that to true, and this is called by the UI when the mouse clicks on the goal. Okay, so you don't have to worry about when this is called, it's just called for you. So I've said, okay, set the start and goal locations, empty the path, everything else you have to do yourself. So if you have to reset the closed list, reset the closed list, reset the open list, and add the root node to the open list inside startSearch. That's it. Next we have isLegalAction. isLegalAction takes in the XY state of the current location. It takes in, it takes in an action, which is an array of length 2. So the first element is the x, and the second element is the y. So this is the action to be performed representing the xy movement from its position. For example, 1, 0 is a move 1 in the x direction and 0 in the y direction, moving right. For this assignment, the only legal actions should be those, but those are already here for you in actions, this.config.actions. So what you have to do in isLegalAction, create the next x and y by adding the actions x and y to the x and y. Then check this.grid.isOOB. I'm just going to leave it named grid. I'm not going to change it now because all these comments say that. If it's out of bounds, then return false, because this new state is out of bounds. You can assume that the one that's passed in is in bounds, right? Because your code is only going to be working with inbounds ones. And then check if this.grid.getXY. If it's the same, then it's good. If it's not the same, then it's not. So this will just return an integer. If the integers aren't the same, right, it's not a color code, it's just a 0, 1, or 2, whatever. If they're not the same, then return false. Otherwise, if nothing made it false, then it's true. Okay, so that's isLegalAction. It's much simpler in this assignment than it will be in assignment 2, where we have octile actions. Now we get to search iteration. Search iteration is where you'll be spending most of your time. So let me, I'll do that one last. So I'm just going to skip over that for a second, because there's 2 more functions. Well, there's search iteration ID-DFS. I'll get to that in a second. 2 other functions that are used by the UI. One is getOpen, the other is getClosed. Currently, these return blank arrays. Because your open list and your closed list could be any arbitrary data structure, the UI needs to be able to get the states that are in the open list in order to draw them, and the states that are in the open list in order to draw them. So for example, this wants an array of unique XY states that are currently in the closed list. If you just so happened to use an array of XY states to store your closed list, then you can just say return this.closed, because it's already in the correct format needed. But if you use some sort of dictionary or other hash table or whatever to do your closed list, then you are going to have to iterate through that somehow, find everything that was there, and then put it into an array as this expects so that the UI can properly draw it. Okay? Same thing with the open list. But just keep in mind that the UI only cares about drawing states. The open list stores nodes. So if you have an array of nodes, you can't just return an array of nodes. Okay? You've got to iterate over all of those nodes, extract the XY states, and build exactly what it wants. You'll know because there'll be an error in the UI if you did it wrong. Okay? But this, so for example, let open equals blank, and then somehow you're going to say open.push xy, sorry, not xy, xy in an array. So you're going to look at each element of the open list, get the nodes x, get the nodes y, and then push them into that, and then you return that open. That's how you do that there. So those are the only other 2 functions. So let's get into the meat of it, which is the search iteration. So let's see what it says. This function will perform 1 iteration of search, which is equivalent to everything inside the while true part of the pseudocode in the class notes. We already went over that. The only difference that being when a path is found, we set the internal path variable rather than returning it from the function, like we did in the pseudocode. When expanding the current node, you must use the this.isLegalAction function above. So when you're expanding and you're saying, hey, is this a new valid state, you must use that function that you wrote. If the search has been completed, path found or open list empty, then this function should do nothing until the startSearch function has been called again. This function should correctly set the this.inProgress variable to false once the search has been completed, which is required for the GUI to function properly. That basically means this. Here, it says, if the search is not in progress, return. That just means if we're currently not searching for anything, it does nothing. That's it. So that's already done for you. Same thing with this one down here, the ID-DFS. If there's no search in progress, do nothing. Okay? This function should perform 1 iteration of BFS if the this.config.strategy variable is equal to BFS, or 1 iteration of DFS if it's equal to DFS. And the tip again, you can use a JavaScript array to represent a queue or a stack. So array.push_e, that pushes an element to the end of an array. Pop takes it from the end, shift takes it from the front. Okay? Even though shift is super convenient, taking something from the first element of an array is not necessarily the fastest thing in the world. Right? So get everything to work using shift, but if you really want to, try and match the speed that I had for the solution, then you may not be able to use shift. But it'll still get you 100% in the assignment if you use shift, because it's fast enough. So let's look at search iteration and what it's doing. So let's look over here again. If I refresh and I take the student BFS and I click a start and I click a goal, okay, how is it doing that, right? Well, all I've done as a sample for you is I've taken the difference in x and y between the start and the goal, And then for each of the differences, I push that difference into the path. Right? So that's all I'm doing right now. I say, what is the difference between the start and the goal? Well, okay, the goal is positively ahead of the start. Maybe there's like a difference of 15, so it just pushes 15 actions of moving right, and then it does the same for the y direction. That's it. It just finds it out and it makes a for loop. All that does is it shows you how to use this.path. That's it. So the first thing you're going to do when you get the assignment is that. Okay? Because it's just there as sample code. You're never going to use it again, and it's false. So don't do that. Now, one thing you are going to do is use this code. So this already has for you, if this.config.strategy is BFS, do the BFS. Otherwise, do the DFS. So something you can do here is just say something like let node equal null, right? Because we don't have it yet. And then if it's BFS, node equals this.open.shift. That's it. That's how you get the node from the open list if it's BFS. And the other line of code, I'll leave up to you. All right? Just pop instead of shift. Really easy to do. So I've done that for you. And then the rest of the algorithm, other than how you get it from the open list, is the same. So all the other parts of the algorithm you would just put down here. Right? Then you would say something like if node is goal. How would you figure that out? Well, we have this.gx and this.gy. We have node.x and node.y. Maybe compare those. And if it is the goal, then what we would do is we'd find the path, set the cost, and most importantly, we would do this.inProgress equals false, right, to stop the search. And then we don't want to go any further and do the rest of the stuff, so we return there. What? No, I don't want this.return. Return. So when you find a path, or when you see that it's empty, make sure that you stop the search by saying this.inProgress is false and then return. And so that stops the function. And then down below that, you just do the rest of the function, which would be the rest of this, right? So if it's the goal, find the solution. Otherwise, if it's in the closed list, return, because we don't want to do anything that's already been expanded. Add it to the closed list, and then expand it, so add the children of this one to the open list. And the only remaining thing is the ID-DFS, and because it's so much different, it's much more different than BFS and DFS, you're going to have some extra logic there. So the very first thing that I say here is just if this.config.strategy is equal to ID-DFS, then call the other function, then return from this function. So if it's ID-DFS, that's where all this code does. And I've given you some tips here as well. Lots of tips in this assignment. Oops, dictionary. I didn't want to open that. So the things you have to do is, the main thing that's different is when you check to see if the open list is empty. Because when you go to, if the open list is empty, it was either one of two cases. It's either empty because you ran out of depth, or because you didn't run out of depth, and now you have no solution. So at some point in here, if you have a cutoff, so you're going to have to be testing the nodes. So once you get the node out of the open list, like let node equals whatever from the open list, you're going to say, is the depth of the node greater than or equal to my depth limit? If it is, then return. Right? And so you're going to have to record, okay, that was a cutoff, so maybe you have a class variable that records that somehow. And then in here, if it was a depth cutoff, then what you're going to have to do is reset the closed list and reset the open list. Okay? Now, it may actually be kind of tricky to get the closed list working for ID-DFS. And I wanted to include a note here, but for some reason, Google Drive overwrote the code, the note that I wrote last night. So I am going to write a D2L post specifically about the closed list in ID-DFS, or when you get this assignment later tonight, it will be in there for you. But it may be a little bit tricky to get the closed list working for ID-DFS. I'm not going to give it all away, because you're grad students, and I want you to sort of, figure this out. So I'm not giving you the exact code, but for example, every time you put the depth up one, one thing you have to do is reset the closed list, right? Because if you don't reset the closed list and all the nodes around, or all the states around the starting node are in the closed list, the very first thing you'll do is that the starting state is in the closed list and you stop the search immediately. So every new depth is going to have its own closed list. You're going to regrow the closed list, etc. And then implement the rest of the algorithm. So that's going to be like breadth first search should be no problem. You're probably going to do this assignment and run into one case where like, oh, my closed list didn't work properly, and so let's just show you something. So you're going to run into a case maybe where you try to make a path and then the browser freezes. Super annoying because now you can't use the website. Like it's infinitely looping and there's no shortcut to stop the JavaScript. So in that case, what you should do is take this, copy it, open a new tab, paste it, and open a new version of the website. Or double-click the HTML file again. Then for some reason, especially in Chrome, I've found this. Closing the tab that's infinitely looping is a bit of an art. It's weird. So if this tab is the one that's infinitely looping, I can be jamming on that X, and it doesn't do anything. It won't close it because the JavaScript is currently running. But this is for your sanity, which I found that works. If you go to another tab that isn't infinitely looping, the JavaScript for this page is now paused. So non-active tab JavaScripts are paused, and now if I hit X a bunch of times, it will actually close that tab. So open up a new tab to sort of pause the JavaScript, then jam on the X until that other one closes. I know it's annoying. Everyone's going to run into it at least once, probably. And if you don't have the closed list implemented, then if you try and like search for this path without a closed list, it's gonna it'll take infinite years, right? We talked about that infinite problem with BFS until we introduce the closed list. So there's that. The last thing I'll do is in here we have a marks file. So I try and be as exact as I can with the marks file. So I always have 5% is either free or taken away. And that's for like coding style. I want your code style to match the coding style that I have in there. So use the same sort of braces. Don't have a ton of like white space between code. It doesn't have to be, you know, John Carmack writing this code or any other guru, but it should look nice, right? One thing here, we're going to take off a % or two. All this to-do stuff in Search Student, the only comments that should be remaining in your code are to explain your code if you did something wacky. So all this stuff, please remove that. It just makes me scroll extra when we're grading. So that's the marks. Data structures, there's 10% for properly, using a stack or a queue for the BFS or DFS. Other functions, this works properly or it doesn't. BFS, all the test paths. Oh, so here for the default tests, currently the solution runs in 50 milliseconds. I've said that each of your paths individually have to take less than a second, which they should. Like if it's working, if your closed list is working, you shouldn't have to worry about the timing. But there is 2% of this assignment reserved for your tests working on this map. Okay? So if your tests work on that map, if they don't work on this map, you'll get a 98. So if you want the 100, you've got to work for it by optimizing your code a little bit.